I wanted to address two concepts, and these are just additional videos, so if you want extra clarification, they're there for you. If you understand this, then don't worry about watching this in the next video. The first one is going to be on forces, and I'm taking from a quiz question, but not with the same numbers, just to kind of demonstrate the concept from there. I was asked this question on Friday during lecture, I'm sorry, during your quiz time, and tragically, I thought the student was asking about the center charge and the net for what the charges for 1 and 3 needed to be for 2 to be stationary. And let's see how that came out, and we'll see why that question made no sense. So if I look at what's happening with this negative 5 nanocoulomb charge, Rika, enough. This negative 5 nanocoulomb charge, in order for it to stay stationary, what must be true? Well, we know that the two sides are equidistant. So the Q on the left and the Q on the right are the same distance from the middle one. And I know that, let's see, if they weren't the same sign, what would I have? I'd have like an attraction to 1. So say that the 3 was a positive and the 1 was a negative. So this would be like force 3 on 2 if 3 is negative, positive, sorry. And if 1 is negative, well, if I look in terms of a negative and a negative, well, 2 is going to be repulsed from 3. So I'd have the same direction. I'd have F1 on 2 here if 1 was negative. If I want something to stay in equilibrium, the one thing I can't have is net forces, right? Because then I'd have acceleration. And if they're opposite signs, then I'm definitely going to have acceleration. I have just 2 vectors. I definitely have a net force. So this is not in equilibrium. Okay, now if they're different sized charges, I'm going to end up with the same thing. So different size, but same charge. Different size. Q, same charge. So either both positive or both negative. What would I have? So here is my center charge, and let's just call 1 and 3 both positive. So it's going to be attracted to both. I'm going to have a force vector going like this way and a force vector going like this way, but one of those vectors is going to be larger because remember, we define the force between 2 charges as being the electrostatic constant and the magnitude of each charge times itself, or times the other, divided by the distance squared. So if Q1 or Q3 is larger, I'm going to have a larger force vector. So this also would not be in equilibrium. So what I'd have to have is 1 and 3 equal in size because they're the same distance. Now I could change the distances to allow for different magnitudes of charge. That would work. But if I want things to stay put, I have to have book-ended charges that are the same sign. Otherwise, we're going to end up with acceleration like we did here. So going on them wanting to be in equilibrium, they have to be the same size and same charge, and I'm going to have like this thing going on. And then we wrote out our sum of forces. Sum of forces. What do I have here? It's all in the x. Let's define up and to the right as positive. So it's all in the x. I'm going to have, let's see, force 3 on 2. And then, actually, that would be minus. I should have labeled that. Oh, no, it's attracted. I made them positive. Okay, so this would be force 3 on 2. And this would be force 1 on 2. So force 3 on 2 minus force 1 on 2 And for this thing to be in equilibrium, that equals 0. So that means that my force 3 on 2 equals my force 1 on 2. And now I can put in Coulomb's law. So I'll have like K Q3 Q2 divided by R squared equals K Q1 Q2 divided by R squared. And this is the part that should have been the red flag in my head to say that we were focusing on the wrong two charges. Because when I look at this, what did we decide? That Q3 must equal Q1. And this is a must. So if that's the case, let's see, my distances are the same, my K's are the same, Q2 is the same. Well, all I did here is say that Q3 must equal Q1, which is kind of like what we came up with here, right? Well, that's not helpful, because that just says that this can be any charge. Any charge at the same distance will create that equilibrium. That means that any of the answers would have been good. What the question was looking for is what must Q1 and Q3 be for Q3 to be in equilibrium? That one actually makes more sense because it's just not an answer of anything, right? So what do we have going on here? So this would be looking at, let's be clear here, looking at Q2. Looking at Q2. So now let's look at Q3. What's going to happen there? So here's my Q3. Well, let's just call it a positive charge for fun and say that it is therefore going to be attracted towards Q2. So this would be force 2 on 3 and repulsed by Q1. So force 1 on 3. Because we're just looking at it interacting with the other two. So that's it. Now, what do I know about those two things? For 3 to stay static, that means this force 1 on 3 and force 2 on 3, they both must be equal. Otherwise, I have acceleration one direction or the other, whichever one is larger. So now I can do my sum of forces here. So I'd have my sum in the x says what? If I go like this, again, just sticking with to the right and up as positive, I have force 1 on 3 minus force 2 on 3, and that must equal 0. So let's move the one force to the other side, set them equal to each other, and see that this also cleans up nicely. Q1, Q3 divided by R squared. So this is between 1 and 3. Well, I've defined this as 1 and this is 3. I'm going to go ahead and write in what that distance is now. So I don't inadvertently cancel out my R because it is not the same. It's not the same between the two. So I'm going to have my 2 meters squared. And that's going to equal, I'll come to the other side, KQ2 on Q3 divided by that distance squared, which I just made easy for myself. It's just 1, so squared. Now I can cancel things out. Let's see, I can cancel out my Q3. I can cancel out my K's. I just made my button pushing easier. What do we know? We know what this charge is. So let's come over here and go, well, we want Q1, so all I need to do is move the distance to the other side. So I'll go Q1 then is going to equal my 2 meters squared times Q2, which I made here 5 nanocoulombs, so 5 times 10 to the negative 9 coulombs, divided by that 1 meter squared. So for the example I just created here, so I have 4 times 5, so I have 20. Meter squared cancels out with meter squared, so I'm good there. I'm going to be left with units of just coulombs, which is good. So 20 times 10 to the negative 9 coulombs, or 20 nanocoulombs. Done. I could do the same thing for 1. what we know is that I'm going to have this symmetry going about the 5 Coulomb charge, right? So if I were to focus on, I'm sorry, so this comes out with Q3, we want Q1, we want Q3. Get my brain going with all these numbers. We know Q1, but we also decided up here that Q3 must equal Q1. So I also have that because Q1 equals Q3, I am done. They both equal this 20 nanocoulombs. Those forces must be the same. Otherwise, I'm going to have my 5 nanocoulomb charge fleeing. If that's fleeing, then everything else is moving. So everything would be accelerating. I can't have static equilibrium for one if everything is off balance for everything else. So a more realistic question for this would be like 2 parallel plates, and I have the one charge in the middle. One charge in the middle is being suspended. What do these 2 plates need to be to make that happen? Or what does the charge on this plate need to be such that it is balanced out with the attractive force from the middle and the repulsive force from the other end? So those are things we can figure out. Now let's go on to our electric fields. Control Shift S.